today for the last talk. Bethany obtained her PhD under the supervision of Latent and also Steve Branton at the University of Washington, where she worked at the intersection of between deep learning and linear dynamics mostly. And she's currently working as a computer scientist at the Argonne National Laboratory. I think she has done really exciting work in the use of deep learning to learn embeddings of linear dynamical systems, and she has done very beautiful work. I'm really a fan of this in the data-driven discovery of equations of motion, which I think will be her presentation today. I think her talk will be a really good follow-up for what Gabo Mindil presented yesterday. So I'm really glad to have her here today for this talk. And Bethany, whenever you like. Thank you.
Thank you. Yes, so I'm at Argonne National Lab, which is in the Chicago area, and specifically at the Leadership Computing Facility, which is our supercomputer facility. And this paper that I'm going to talk about is joint work with Kathleen Champion, Nathan Kutz, and Steve Brunton at the University of Washington. And I'd like to highlight that Kathleen Champion is the first author, and she's currently working at Amazon after finishing her PhD. And before I talk about the project, I wanted to give you a quick advertisement. So I know you've been learning some about data science and machine learning, and if you've been wishing that you had more CPUs or GPUs for your scientific machine learning, I'd encourage you to consider applying for time on our computers. The deadline is January 29th, and you would get free time on our computers plus staff support. So you would be assigned 1 or 2 people from my team as your point of contact. And if you're interested, I'd recommend start thinking soon. You can apply for a small allocation to test out your code to prepare for the application. And I'd be happy to talk to you later. And similarly, if you're excited about scaling deep learning, we're hosting a free virtual workshop next month, but you need to register by Friday to participate. And it's designed to learn how to scale up your machine learning, particularly on our machines, and prepare to write a proposal for time on our machines. Okay, so back to this paper. Our goal is to turn your high-dimensional scientific data into parsimonious dynamical models. And by parsimonious, I mean simple, easy to write down, not complicated with lots of terms. So the examples I show here, one is a video of a pendulum. And if you just take that video data, it's very high dimensional because you have all those pixels. But we know that what's happening is really just this simple equation in terms of the angle of the pendulum. We'd like to be able to go from the video to project down to this angle and know what the equation is in terms of the angle. At the bottom here, I have a fluid flow, which would also be high dimensional, but is governed by one PDE, the Navier-Stokes. And maybe even more ambitious is brain data, where we just really don't know the equations. So to drill down a little bit more, let's say you have this video of your pendulum. So it's in high dimensional pixel space. We want to learn, we don't know what the underlying dynamics are, but maybe it looks like it should be simpler than the full pixel space. We want to learn how to go from high dimension to some low dimensional space and simple equations in that space. In order to do that, we need to identify new coordinates for the pendulum that would ideally be the angle and the parsimonious dynamics in those coordinates. And our method is to solve both of those problems at once. So use deep learning, specifically an autoencoder, to identify coordinates, and the Cindy method to model dynamics. And I'll talk about what the Cindy method is. So why would you want to learn dynamical models? Well, I think this audience is probably already interested in this, but perhaps you have a lot of data, but you don't know simple models to describe what's happening. Also, if you could learn governing equations, they would probably generalize really well. And once you have a mathematical model, you can apply all the dynamical systems theory and analysis that you already know. Or maybe you want to do prediction, some kind of simulations, and a simple model would be faster than a complex one. And perhaps most importantly, if you want to have a real insight on the underlying processes, we would like something interpretable. So that was why we want to learn dynamics, and why you would want to learn new coordinates is if we tried to write equations for the pendulum in pixel space, they'd be high dimensional and complicated, not very interpretable. And even if we're already low dimension, it could still be inconvenient coordinates. So if this is a sketch of a pendulum oscillating under some ceiling, some bar. And if you measured your pendulum in terms of XY coordinates, that's already low dimensional, but the equations would be complicated. And the equations are so much nicer if you know that you can write them in terms of the angle of the pendulum. And why do we want to jointly learn these? Well, there's a lot of ways to do dimensionality reduction, such as the singular value decomposition, which you might call PCA or POD. You could do an autoencoder. There's different ways of doing reduced order modeling. You could project the same data to a low dimensional space in a lot of ways, but there might not be simple equations there. Just like how the pendulum in terms of XY coordinates is low dimensional, but doesn't give you simple equations. And so we want to solve both of these problems at the same time. So not just any low dimensional coordinates, but specifically ones with simple equations. So first I'm going to talk about the Cindy algorithm because we're going to use it in our method. So Cindy is short for Sparse Identification of Nonlinear Dynamics. And it's from this 2016 paper in PNAS by Steve Brunton, Josh Proctor, and Nathan Kutz. Steve and Nathan are at the University of Washington, and Josh Proctor is at the Institute for Disease Modeling. And as mentioned, I worked with Steve and Nathan during my PhD and postdoc. And the idea is that you have some time series data X that came from some dynamical system, some ODEs, and you don't know what the ODE is, you want to find it. For example, you might be familiar with the Lorenz equations. So we have this three-dimensional system. We can write down these simple equations, and this is what its attractor looks like. And this comes up as a nice simple example of chaos emerging. And so I'm going to use Lorenz as an example to explain the Cindy method. So in the Cindy method, first you need to collect your data X, so some time series data. And then you need to either collect the derivatives or estimate them. And for Lorenz, there would be three variables, three time series that you're collecting, and you stack them up in a matrix. And I should note that it could be multiple trajectories. It doesn't have to all be one trajectory. You could have different initial conditions. You just stack them up. Then we need to guess what kind of terms would show up in the differential equations. And a lot of differential equations have polynomials. So here we're guessing that we are interested in monomial terms up to degree 3. And so you have your data x1, x2, x3. You stack it up in this matrix, but also the monomial functions of your data. So this matrix theta we call the library. So it's like all the options you could use to construct your differential equations. And then we have this matrix Xi, which contains the coefficients. And the idea is we assume that we can write down equations where the derivatives are some linear combination of these library terms. Now, there could be a lot of ways to fit this data as linear combinations of these terms, but we want nice equations. We want them to be simple, easy to write down and talk about. So we want as few terms as possible. And so that's where the sparsity comes in. We want this coefficient matrix to have as many zeros as possible. And here it's colored in 7 places, and those are the 7 terms that we actually want for the Lorenz system. And at the end of the Cindy method, you have identified your system. Each of those columns from ESCUELA tell you which terms are in that equation. And remember, we're assuming that we didn't know the equations ahead of time. This is just an example with the Lorenz system. Okay, so how does the algorithm actually work? So on the one hand, we want to model your data with this linear combination of monomial terms. That's this left part. You want it to be accurate. So you want your linear combination of library terms to be close to those derivatives. But on the other hand, we also wanted lots of zeros because we want simple equations. So you have these this accuracy and sparsity to trade off as 2 goals. And this can be written down as a convex optimization problem. And if you've seen Lasso, this should look familiar to you from statistics. So we want to find the coefficient matrix C that minimizes this objective. We want to minimize accuracy and sparsity. And the norm that counts the number of non-zero terms in a matrix is the 0 norm. We don't want to literally use that because it's NP hard to solve this problem with the 0 norm. It's not a convex problem. And so what's commonly done in statistics and mathematics is to approximate this with the 1 norm, which is the sum of absolute values in the matrix. So that's those 2 terms. We have the accuracy term and the sparsity term. And we have this parameter lambda to trade off those 2 priorities. And so this is the idea. And you could solve this problem with multiple sparse regression techniques. And in the original paper, they said in practice, what they found most useful is an approach called least squares sequential thresholding. So they actually solve the accuracy problem first, which is just a least squares problem. It's just a linear problem. Then threshold the small coefficients to 0 and iterate. And there's some follow-up work comparing different ways to solve this sparse regression problem. But the important part is Cindy reduces this very complicated problem where there's exponentially many options to something that can be written as a convex problem and solved with various sparse regression algorithms. The success of the Cindy algorithm depends on the measurements you took. So if you wanted to learn the Lorenz system, then hopefully you were measuring x1, x2, x3. You also need good quality data. So if you have enough noise, that will eventually kill you, especially because we need to estimate those derivatives. And you need to be able to guess what should be in the library. A good starting point would be polynomials, both because they're common in the differential equations we already know, and because at the very least, maybe you're learning a Taylor approximation. But maybe if you have domain knowledge, you can put something else in your library. So to summarize the 2016 paper on the Cindy algorithm, you assume you have time series data. Your goal is to learn simple governing equations, some ODEs. You assume there are few terms in the equations, and you approach this with sparse regression. And if you want to try this, you can collect time series data from your own problem, estimate the derivatives if they're unknown. The Cindy paper talks about how they tried to do this in a smooth way and avoid amplifying the noise. You need to choose your library of potential terms. And if you go to Nathan Kutz's website, you can see the original MATLAB code. But if you're used to Python, there's now a very nicely written PyCindy library that you can find on GitHub. And it includes multiple methods for the sparse regression. And I just want to highlight some of the follow-up papers. So one is, okay, there was that parameter for how much you emphasize accuracy versus sparsity. In this paper by Neil Mangan, talks about a formal way to trade those off and pick between different models with an AIC criterion, which you may know about from statistics. Sam Rudy wrote a paper with a version of Cindy for PDEs. The original paper was about ODEs. Neil Mangan also wrote a paper with an implicit version of Cindy, which allows you to learn rational functions, which are important in some fields of biology. There's also Steve Brunton wrote about extending Cindy for control problems. Kathleen Champion wrote about good sampling strategies to choose that time series data when you have multi-scale systems. I think this is pretty cool because she shows that you need pretty short trajectories in order to get the right dynamical system. And J.C. Lassou and Steve Brunton wrote about how to incorporate the physics you already know as constraints. Does anyone have any questions about the Cindy algorithm before I move on to how we extended it?
I have one actually. So you mentioned that you need to be very careful with the coordinates you choose. And you mentioned that, well, if you work with a loaded system, for example, you rather choose x, y, x2, and x3. But I mean, why, if you have a linear combination of those, if you have like any other variable? So my question is, why is it so important? The choice of coordinates, in principle, or why could you fail if you don't choose the coordinates wisely?
Yeah, if you don't choose them wisely, you would probably get overly complicated equations. So if you choose them well, then hopefully you can find simpler ones. So with the pendulum, if you put in the XY coordinates, it is possible to write down ODEs for the pendulum in XY coordinates, but they'd be long. Right.
Okay. So, but this will only work then if you already do some kind of feature engineering, so to say, to choose the right coordinates. Like you wouldn't expect this to work with the XY coordinates for the pendulum, for example.
Yeah. So that's what we talk about for our extension, is how to choose good coordinates, learn good coordinates. Yeah.
Pablo is asking, how does the time scale with the name of basis functions you choose for Cindy? So you could choose a lot or a few polynomial terms. How does time scale with that?
Yes. Well, I think that's a good question. I think that would boil down to the sparse regression problem you pick. So if you think of, the sparse regression algorithm you pick. So I'm not sure if it would be a little linear or squared. But if you think of like solving a least squares problem, yeah, we can get back to that.
Right. And Cindy is asking if you have a set of possible starting equations or so how do you choose them? I think that's her question. So you say you started with the polynomials, but then of course you could miss something.
Oh, yes. So this would be, if anyone's interested in a project, this would be really cool follow-up work, is a smart way to add on to your library when you have some partial results. So if you're missing something, I think it's probably going to pick the Taylor series approximation of what you're missing. And it would be very cool to have an automated way to fill that gap. Like, We must be missing a sign term or something like that.
So you say, for example, in the pendulum with large amplitude deviations from the vertical, if you don't use a sine function in your basis, but you still keep adding polynomial terms, eventually you will converge to the Taylor expansion somehow.
Yes, yes.
Okay, that's
I
cool.
think that's what would happen.
Yeah, excellent. And Ignacio's asking, so of the follow-up papers you showed, which of them are dealing with noise terms?
Let's see. So I think none of these ones I'm showing here explicitly talk about noise. They're in the original paper. Oh, actually, I think this sampling strategies paper, I think it talks a little bit about the noise. In the original paper, they talk a little bit about using TV diff, I forget what that's, total variation something, to smooth out derivatives. And I believe there's a paper from, I think, Hayden Schaefer about looking at the integral terms instead of the integral form instead of derivatives, so that you can, you don't have to amplify the noise by taking derivatives. And there's probably more work, I just don't know off the top of my head. That's a great question.
Okay, so I don't think we have more questions with that, so you can go on.
Okay, great. So that was the original SINDI method from a few years ago. And as I mentioned, in our work, we wanted to also solve the problem of learning new coordinates. So going back to this example of a video of a pendulum, we don't want to learn the equations in terms of pixels. We want to learn that we can map from pixels to the angle, and then learn equations in terms of the angle. And I also have here an animation of a reaction diffusion PDE, which is high dimensional spatially, but actually it has just very simple oscillations happening. And we use deep learning to find the new coordinate transformation. And this is because due to the universal approximation theorem, roughly a neural network can approximate any reasonably nice, smooth function arbitrarily well. So you have some hope that if the coordinate transformation exists, it's possible to represent it with a neural network. The hierarchical structure of deep learning of these layers saves on parameters over something like polynomial regression. And we have some idea that in deep learning, you don't need to be as careful about the features or basis or your in general input representation, because the deep learning is sort of learning features for you. These earlier layers sort of learn features that help the later layers. And so these are points that are general pros of deep learning, but also specific to why we wanted to use them. And I know you've been learning about neural networks this week. I don't know if you've learned about autoencoders. I think you probably did, but just in case, an autoencoder is a particular kind of neural network where you want the output to be the same as the input. And I know that sounds dumb at first. The idea is you added some extra constraint. Most commonly, in the way we use it, is that we have some middle layer that is low dimensional. So here we colored it yellow, and I call it Z. The earlier layers going from X to Z are called the encoder, and we're going from high dimension to low dimension. The later layers are called the decoder, and you go back from low dimension to high dimension. And then the output is a reconstruction of your input. So your loss function is that you want the reconstruction to have low error. You want this output to be similar to the input. So you're essentially finding some low dimensional representation of your data. You can think of this as analogous to a nonlinear PCA, or maybe you call it SVD or POD, except since it's nonlinear, it can be more expressive. than an SVD. So this is a general type of neural network, and it's what we want to use because we want to find new coordinates. And since they're new coordinates, we want to be able to get back to the original coordinates. So what we know is x, we want to find some representation z and be able to get back to x. But like I mentioned, we don't want to find just any new coordinates z. We want new coordinates where we will have simple equations. So on the left, we have this autoencoder reconstruction loss, but we also want to solve the Cindy problem in these new coordinates z. And so here I'm just repeating the Cindy loss function again. We have a library of terms, but this time it's in terms of z, this middle layer, the output of this middle part of the neural network, this low dimensional representation of our data. And so again, we have this trade-off between that model in terms of z should be accurate, but we also want it to be sparse, have lots of zeros. And part of the tricky thing here was how will we calculate this loss function? But in neural networks, we already know, we know the structure of our layers and we know how to take derivatives. And so to take the derivative of z, our new coordinates, in terms of x, the input, that's just like taking derivatives through these layers. We know the form of the layers. We can write this down. We can use our TensorFlow library. And because of the chain rule, we also still need those estimated derivatives of x. And so the library term, here we're plugging in z, the output of the encoder, instead of our original data x. And we're still learning this coefficient matrix C. Okay, so this is what we thought at first. We'll just combine the reconstruction loss with the Cindy loss. We found that the neural network basically tries to cheat though. In practice, it realizes, oh, if we make z coordinates really small, these derivatives are small, then this loss function gets small even though the equations are wrong. So to counteract that, we needed a third loss term. And this, I know this looks even more complicated and ridiculous, but what we're essentially doing is saying that the equations need to be correct back in x coordinates as well. So if you look at the reconstruction of x and take that derivative, it should match those x derivatives we know. And again, we can do the chain rule and calculate these derivatives because we know the structure of our network. So don't worry about that weird equation. But the high level idea is we have all these losses we need to balance. We want to be able to reconstruct our data x, which means that those z coordinates were a legitimate coordinate transformation. We need the equations we're learning to be correct in terms of x and correct in z coordinates. And we have this sparsity term. And I wrote this down as a L1 penalty on ICSI, which is a standard a standard function in neural network frameworks like TensorFlow, but in practice, it will make a lot of the entries very small, but not actually zero. So just like in the original Cindy paper, we added this sequential thresholding. And here that means we had the L1 penalty, and then we would go along training and periodically pause to threshold the small coefficients to 0, and then continue training. And we used a mask so that those ones that were thresholded to 0 cannot come back. And again, this is there could be multiple ways to handle the sparse regression, but this was one approach that worked well for us. And we talk about 3 examples in our paper. The first is Lorenz. So we we know the Lorenz equations. We want to rediscover them, but in a high dimensional space. We also want to find a reduced order model for that reaction diffusion PDE, which is just oscillating. And then this example of being able to find the pendulum in pixel space. And what we're most interested in is that the sparsity pattern is correct, so it chooses the correct terms, because we can always refine from there if they're a little off. And for each example, we ran the training 10 times. So if you've been using deep learning, then you've seen that deep learning depends a lot on how you randomly initialize the weights. And so what we did here was we run it 10 times. That gets us 10 models. And then we pick the best based on, again, balancing this sparsity and accuracy. Okay, so first example, Lorenz. So we know the Lorenz equations, and we projected them up from 3 dimensions to 128 dimensions. And so if you call the coordinates, the true coordinates of Lorenz, Z1, Z2, Z3, then the way we defined the high dimensional version was a linear transformation of Z plus B times the cubes of those Lorenz coordinates. And so I can't plot for you 128 dimensional space, but here we stack up those 128 dimensions as if it's like space versus time. And so you get some idea of what the dynamics look like. But we know, because of the way we defined it, that inherently the only thing happening is the Lorenz dynamics. So the input to our neural network is this 128 dimensional data we made up, and we want to recover the Lorenz system. So to remind you, on the left here are the true Lorenz equations that we used. And in this coefficient matrix, the 7 terms we actually want are colored in. And this is what the attractor looks like for the real system. And we used our method and we discovered this model. And it has 7 terms, but it's a little off. We found that it's actually an affine transformation from the how we normally write down Lorenz up to this scale factor. So here we have some non-uniqueness in how the Lorenz system could be represented, but we are able to essentially recover a transformed version of Lorenz. And I mentioned that we do the training 10 times. So to give you an idea of the variety we see, the coefficient matrix had 60 possible terms, and we wanted to learn 7. Sorry, I had to refresh my memory. We wanted to learn 7, only select 7 of those 60. And we found twice it picked 7, other times it picked more. And again, we can pick the best of these options by balancing sparsity and accuracy. Okay, our second example was the reaction diffusion PDE. And so if you solve this PDE model, you have something that's high dimensional in space. But we see there's a very simple behavior happening here. In one model that we find underlying here is this simple linear model with an oscillation. In another model that is just as sparse and similar accuracy, but a little different, is a linear oscillation. And so this is cool that we can go from something as high dimensional as this animation to something 2-dimensional. And our third example is the pendulum. Now, we didn't use a real video of a pendulum, but we animated a pendulum oscillating back and forth in pixel space. And we want to input these pixels to the neural network and recover the pendulum equations. And it's pretty exciting. It successfully finds that it The important thing is the angle. It picked 0.99, which is awfully close to 1. It picks just one term, sine, and the attractor looks correct. And to give you an idea of the variety, here another model it picked when we ran 10 times is this linear model, which is just as sparse, but definitely less accurate. And you can see in the paper, one way to validate the model you found is to simulate forward, and you can see that this is very, it's just clearly less good than the other one. Okay, so people often ask us how you choose the size of the latent space. So the size of this underlying model you want to discover. And here you have a complexity versus accuracy trade-off that you probably see in a lot of modeling problems. We want to pick the simplest model that is accurate. And you can, so you could vary the size of the latent space in some range, and then pick the lowest dimensional one where you're still satisfied with the accuracy. Those of you who use PCA or POD are probably familiar with these kind of trade-off curves where you pick the least number of modes possible while still achieving some accuracy. In modeling, people often talk about something like a Pareto front, and so you can see this drop off where your error suddenly dives off. It gets really low, and you're like, okay, I want that elbow term where it just got really accurate, but is not overly complicated. And if you wanted a starting point, you could train just a normal autoencoder, which is just finding some low dimensional representation of your data and see how small that can get. The autoencoder would be something a little faster to train, and then use that as a starting point. So the Cindy autoencoder might need to be higher dimensional in order to have those good equations, but at least you have some idea of a starting place of how low dimensional the dynamics really are underneath your data. And something that I think is really cool about this research is that at the end you have these interpretable dynamical models. You have an ODE to write down. And a lot of people talk about machine learning as black box in contrast with physical models, which you can call white box. And they say, well, machine learning is cool, but at the end you don't have a physical model that you can interpret and use all of your math and physics knowledge. So I like that here we could really discover some underlying governing equations from your data and potentially new science. Now, the autoencoder itself is not interpretable, just like any other neural network is difficult to interpret, but the equations may generalize. We talk about this in the paper. So let's say you trained our Cindy autoencoder in some regime of your data, either like a certain domain or with a certain model parameter. If you get the dynamics and you want to see how to apply that to data that's like shifted over or from different parameters, you can fix the dynamics in the middle and just retrain the autoencoder. So I think that is a cool avenue for interpretability or generalizability, I suppose. And this is not in the paper, but since I'm at a supercomputer facility, I wanted to see how well our code scales to a large number of examples, a large latent size. So this doesn't quite get at the question someone asked about the size of the input. But I can show you what I do have. So I looked at the Lorenz example. Now, if you remember in the Lorenz example, it's inherently 3-dimensional, and we project it up to 128-dimensional, just for the point of having an example. Well, so that means we could also arbitrarily project even higher dimensional. So I went to 256 dimensions, and I generated extra data, 4.1 million examples, just for the sake of seeing how well this scales. And I looked at data distributed learning. So that's when you have this big data set and you don't want to put it all on one GPU or CPU. You split the data onto different processors. And if you think about how stochastic gradient descent works, when you're calculating those derivatives, those gradients, you're summing over your examples anyway. So, and really you're summing over one batch at a time. So it makes sense that it's possible to split your data across different processors. You can calculate gradients locally and communicate periodically. And so this is just, this is not specific to our method. This is just in general, you can distribute data for deep learning in this way. And I looked at the Horvath library, which my team loves to use on our computers. It's pretty effective at handling this data distribution. And so here I fixed the problem size to 4.1 million examples, 256 dimensional. These colors are for different batch sizes. And across the x-axis, I increased the number of GPUs I use. And this is a log-log plot for how long epochs take. And it looks like a line. So this is the kind of scaling we'd want to see. And this is really nothing to do with Cindy. It's just that we're not getting in the way of how well Horvath can scale when your GPUs can communicate with each other quickly. So this is the easy way to scale because we have this general solution of Horvath that works for deep learning. And the harder way to scale is to vary the latent dimension. So here I was looking at a polynomial library, and the bigger the latent dimension is, the bigger my library needed to be, given that I fixed, I think I wanted all the polynomials up to degree 3. And that is a factorial growth if you think about the number of combinations of monomial terms. And so the library is growing factorially, and that means the time to do your epochs grows exponentially. This is a log-log plot, and it's worse than a line. So I also tried varying the input, like someone asked, and it was, I didn't include the plot here. It was somewhere better. It was definitely not the bottleneck. The bottleneck, because I was only linearly increasing the input size, whereas increasing the latent dimension causes this exponential increase in the library. And so to give you some numbers here, when the latent space was 3-dimensional for this particular data set and problem, it took 18 minutes to train for 5,000 epochs. When I went to 14-dimensional, it took 14 hours. So if anyone thinks this is interesting and wants to think about how to scale better, that would be cool. I am hopeful because if you're looking for interpretable equations, you probably don't want them to be super high dimensional anyway. And this is also an opportunity for research in how to make the library, how to construct a library efficiently, like someone asked. So the problem here is really that the polynomial library is factorially many combinations. So if you had a clever way to adjust your library, you could avoid this bottleneck. And I also want to point out other limitations and opportunities for research. As I mentioned, estimating the derivatives of your time series accentuates any noise. Probably a lot of you have seen that in your own work. And so if you look at the Python library, they have some, I think at least one way in there for how to try to smoothly estimate your derivatives, but this is definitely an avenue for further research. I pointed out that when you learn these underlying governing equations, you have a nice mathematical model that you can interpret, but the autoencoder still has the same limitations as neural networks in general, as far as interpretability and generalizability. You need to be able to choose a reasonably sized library of terms. So if people have ideas for how to do that automatically, that would be very cool. And in the Cindy method, we can, if you still want it to be a convex optimization problem, we can't learn these parameters like the frequency of sign without losing the convexity. Although if you're doing deep learning anyway, maybe you don't mind having this. We lost convexity by doing deep learning, so maybe you don't mind. I haven't gotten to test this yet, how well you can parameterize the terms in your library, because the original Cindy method is about linear combinations of terms. So that's some food for thought for future research. And if you want to try our autoencoder version, this is the name of the paper. Our Kathleen put her code up on GitHub. It's in Python and TensorFlow. You can reproduce all of our results, and she put up Jupyter notebooks, which make it easy to experiment and try your own data. And I'd be happy to talk, especially if you want to try bigger problems. To summarize, we combined the Cindy method with an autoencoder to identify reduced coordinates and parsimonious dynamics from your high-dimensional data. And this was joint work with Kathleen Champion, Nathan Kutz, and Steve Brunton. Does anyone have any questions?
So we don't have any yet. Maybe okay, so we have one already. Elham is asking, maybe you can see them already, so if you like, you can read them directly from the chat, or I can read them to you if you like.
Oh yeah, let's see if I can.
We have two.
Bring up the
first one is for using sparse regression. Do you know the general form of the PDE? What kind of data can be used to approximate PDE?
So let's see. So Sam Rudy wrote the follow-up paper for PDEs, and he has, and similar to ODEs, you need to kind of guess the terms of the PDE. So you might guess that you want UX, UT, UXX, and so forth. So you don't need to know the exact form of the PDE, just maybe some terms that might show up in the PDE. But to gather the data, so I'm thinking of this as a case where you don't know the PDE, but you just have some data, and you want to find the underlying PDE. But I could imagine if you had some kind of simulation where you wanted to find some similar version of how to recreate, simpler version to recreate that data. Maybe maybe you had some complicated equations and then you use this method to find the simpler version.
So Herman is asking, for each pass of the autoencoder, you feed all the variables at a single time, correct? But CIMI needs the information of many time steps. So how do you handle this?
Yes. Okay, so in this approach, we're actually matching up the derivatives with the time series. So let's say at time 0, you know you have this derivative, and you know you have these terms x1, x2, x3. And so you don't technically need a whole span of time because you're matching, like, this derivative matches with this point in time. So you're in a batch, you might see just some individual time points, and you're not really thinking about the order of them, if that makes sense. Similarly, in original Cindy, when you're stacking up your data in this matrix, you might want to have trajectories lined up, but it's not really taking into account the order of the rows in your matrix. It just knows this derivative corresponds to this point. Does that make some sense?
So I have actually some questions. For example, so this might fail if you really start from projection of the data. Like, for example, so do you have a conical pendulum instead of a Chudin pendulum standard? So do you think this could be capable of inferring that basically you are missing one dimension in the projection?
Yes. So in the original paper, I believe they had an example where you're missing, for example, in Lorenz, you're missing one of the three, and they compensate by adding in time delay coordinates. I believe it's in the original paper. They've definitely tried this at some point. As an approach to compensate for under measuring your data and missing something. And that would be really cool to try with our autoencoder as well. It makes sense that if you had time delay, you could kind of like add on a bunch of time delay coordinates and then shrink back down to see what you're missing.
Yeah, that should work. Another final question for me. Have you ever thought about modifying the loss function so that you can go in the direction of having a variational autoencoder so you can then change the coordinates and generate new samples of dynamics? Maybe that should also help for interpretation of the dimensions of the latent space.
That would be very cool. So as far as having uncertainty, I do know there's some very recent work with Bayesian versions of Cindy, but I think they weren't thinking about the generative aspect of having like a variational autoencoder, which could also be cool if you wanted to explore that latent space. Yeah, that would be cool. We have not tried that.
Matthias is asking about, so you could use previously trained neural ODE to enhance your data in case of time series.
So like using one to create more data, or to...
Yeah. So he's supposed, maybe he can be more specific. Suppose for data augmentation, or in case you have a limited amount of data, I suppose you could principle try to synthetic data combined with.
Yeah, that would be cool. And you could augment your data, and especially when you're in a high-dimensional space, it could be very important to have enough data to really understand that space. And if you're missing some of the important dynamics, then maybe you can't find the equations. It would also be cool to learn like what's missing in your existing equations. So I think Steve has a paper on discrepancy modeling, where what you're learning is what's wrong with your existing system you already know. So you have some like simulation, and you have some equations, they don't quite match up, and so you use Cindy to find the discrepancy.
Cool. So Herman is mentioning that there is a nice and efficient package in Julia, to which he has been contributing also some implementation. I don't know if you knew this, but yeah,
cool.
There's a Julia package. Yeah, there's a GitHub link.
Cool. I think I'd heard of that package, but I didn't realize Cindy was in there. That's awesome. I'll take a look. Yeah. So if anyone uses Julia, that would be a cool way to try.
Okay. So do we have more questions? If not, well, thank you a lot for this really amazing talk. I mean, it's really a pleasure to have. I mean, most of us knew a little bit about Cindy before, but having you, explain it, like first-hand explanation from you is really, really amazing. So that's really excellent talk. So thank you very much. And well, that's all for today. We'll see each other tomorrow morning. So adios. Ciao, ciao.
Thank you, and thanks for the invite.
Thank you. Thank you. Thanks for coming. Bye-bye.